Before we get into that, in order to set the context, let's take a look. Well, first we'll talk a little bit about who GlobalLogic is. We can't get away from this as part of the talk. So GlobalLogic is a product development services company, meaning that we solely do product development. We don't do conventional IT in the sense that we don't do system integration. We do technology integration, obviously, where we put together MongoDB with other technology stack items, but we don't really do SAP, Oracle integration. We focus on developing products for our customers that we white label the products. They ship under our customer's name. We work with medical devices. We work with lots of different companies throughout the world. Our primary development centers are here in India, in Noida. And we're always looking for talent. So this is my first and last plug for GlobalLogic during this talk. When people talk about the Internet of Things, there are two questions I always get asked whenever I talk about it. Number one, it's overhyped. Everybody talks about the Internet of Things, but what are we seeing that's happening? We're going to address that question head on. The second one is, nobody really knows what it means. We all know vaguely that it's something about connecting devices, connecting things, individual items to the Internet. But beyond that, what does the term Internet of Things really mean? And I think by the time you're done with this talk, you're going to see some concrete answers to that question. What we're going to address today is, first, I want to talk about things, and in the spirit of examining the hype around the Internet of Things. So what do we mean by a thing that we might potentially want to connect to the Internet? And what do we mean by the Internet in this context? What has been the evolution of the Internet, and why do we claim that IoT is going to be the next big thing when it comes to the evolution of the Internet, which we do? Then we'll get into a concrete definition of the Internet of Things, and I'll lead you through a practical business example of a real live company that's using Internet of Things concepts as we define them. Then we'll talk about how the Internet of Things is going to change your career, and finally how it's going to change society and change the way that we work when our devices become smarter than we are. So first, let's take a look at the idea about the Internet of Things being hyped. And in the grand scheme of things, let's see, does this work when can you still hear me when I'm away from here? Great, okay. In the grand scheme of things, our capacity to measure everything is very, very limited. So when you take a look at the universe, the physical universe around us, at the universal level and at the atomic level, we have virtually no capacity to manage the everything, right? You often hear the term Internet of Everything for the Internet of Things. I would contend that that term is very much overhyped. We don't have the capability of doing everything. Scientists estimate that the total information content of the universe, thank you, is 10 to the 120th bits of information. Our capacity to store information right now is 10 to the 21 bytes, so approximately 10 to the 22 bits of information, right? So this is a factor of 10 to the 100th less than it would take to model the universe, right? In terms of the number of atoms in the universe, 10 to the 80 atoms in the Earth, stars in the universe, we don't even have enough bits of digital storage information capability today to assign a single bit to every star in the universe, right? We're 200 times less than the number of stars as our total digital information capacity today, which sounds bad in one way, but when you flip it around and you think I believe it's about 25 years, we will have as many bits of digital storage capability addressable on the Internet as there are stars in the entire universe with billions and billions of galaxies. When you think about it that way, it's actually staggering how big our information capability is growing. But as of today, we do not have the capability to model the universe or the atomic level even close. But when you start getting closer to home, we start to have significant capabilities. So when you look at the number of stars in the Milky Way, for example, our own galaxy, we could assign 10 to the 10th bytes of information to each star in the Milky Way galaxy with our current information capability. And similarly, as we move on down, the data generated by a car over its lifetime is less than a gigabyte. The number of items in the U.S. household is 3 times 10 to the fifth, 300,000, 3 lakhs items in which we could assign terabytes of information to each one of those items. Number of stars visible in the sky when you go and look is only about 10,000, oddly enough. So we have huge information capability when we look at the universe around us. When we look at the Earth itself, our information capability is pretty staggering. So the information capability, meaning all the addressable storage on the planet today, is on the order of zettabytes, 10 to the 21st bytes of information. So the number of grains of sand in the world is estimated to be 10 to the 19th. So we could assign 100 bytes per grain of sand on Earth with our current digital storage capability. Now, why in heaven's name you'd ever want to do that, I don't know, right? But we could give you a lot of information about each grain of sand, its location down to the angstrom if we wanted to. In terms of number of trees, 10 to the 11 trees and so on. So these common everyday items, we have ample storage capacity, and we'll talk about compute capabilities and so on in just a second, in order to be able to model these real-life items that are potentially of interest to us. So, for example, just to put things in perspective, we as information professionals deal with numbers like terabytes and petabytes and not so much zettabytes and so on every day, right? So we don't really think about what a staggering amount of capability that gives us in terms of things in the universe that we might want to monitor, things in the world. But my laptop that's sitting over there, like many of you, has about 1 terabyte's worth of storage, right? Now I'm fudging this a little bit because I'm not talking about formatted capability and so on. But there are, for example, 10 to the 11th trees on the planet. And when you look outside, you know, when you're driving here, you think, there's a lot of trees on the planet. So we don't think about us. My laptop has the storage capability to store the location and the type of every tree on planet Earth. So if I had 2 terabytes, I could store it down to the millimeter resolution of the location of every tree, its height, and a number of other capabilities on it. And that's just my laptop. You all have laptops. We have servers on the cloud. Our capability of modeling the Earth around us and the things that are potentially of interest to us, the cars, the trees, the houses, the households, the things in our household, has grown extremely rapidly over the last decades. Another thing that's an interesting thing to look about it is when you look at the total number of things on the planet that we might be interested in tracking, it's on the order of petabytes, peta things, 10 to the 15th things. So given that we have 10 to the 21 bytes of digital storage capability online today and growing very rapidly, we could assign on the order of megabytes to each thing that we'd want to track on the entire planet. A megabyte, we're used to thinking about that nowadays as very small. The PowerPoint file that I'm showing right now is, I don't know what, about 10 megabytes at least, right? But a megabyte's actually enough text to fill a small novel. And all the works of Shakespeare are in about 5 megabytes. So we have the capability of monitoring everything on the planet to a significant level of detail. Some things are obviously of much more interest than others and would require much more storage. But in terms of our overall capability of modeling information, we now have the technical capability of tracking every item of interest on Earth if we're interested in doing so, if there's a business case for doing so. And what my experience has been over the last 30 years, and we'll take you through this next, is that when a technology becomes economically viable and available, it tends to happen, and it tends to drive the next wave of innovation. So let's, just before we leave this thing about the things, when we get to talk about the internet, let's take a look at what's driving these trends. Well, first of all, costs of data storage, of processing capability, of random access storage have grown by factors of 16, 20, over 100 over the last decade. Similarly, and for the same reason, the capabilities have grown. The amount of general purpose storage capability per person on the planet, it grows, it doubles approximately every 40 months. And general purpose storage, general compute power doubles every 18 months. And in terms of connectivity, we now have more phones than we have people on the planet. And more new Android devices are activated every day than babies are born. About 40% of the planet, all of us have multiple phones. I have about 4 phones here at the moment, which is the reason the ratios don't quite add up there, but about 40% of the people on the planet are now connected to the internet. So what does this mean in terms of hype? Okay. Now, in the 1990s, a very much overhyped term, and many of you are too young to remember this firsthand, was the World Wide Web. Everyone was talking about the World Wide Web, how someday everybody on the planet would be able to see all the information that you publish. You could create a web page or information about your business. Everybody on the world could see it. And this was considered a lot of hype. And the reason for this hype cycle, I believe, is because even though the trend is clear, the particular winners within the trend are not clear. Okay, so Google, for example, I didn't apply to Google because I thought, I don't know if they're going to be successful. They're just another search engine, right? Big mistake. But I was at Apple, so I don't know. It kind of evens out. But anyway, in the 1990s, the World Wide Web, trust me, if you weren't there, was very much an overhyped term. Now, what's happened in the last 20 years? Well, these companies were founded in the 1990s, all of them, and collectively, them and their companions have created trillions of US dollars in wealth. So that didn't exist before, right? So even though it was overhyped, the World Wide Web came true, and as I mentioned before, 40% of the world, everybody in the world can get on the internet, theoretically, and 40% of the world does. So it took 20 years, but it happened, okay? Then the next overhyped term that we had to worry about was Web 2.0. So Web 1.0 is one-directional communication where I publish information to you. And there was some interactivity in this in e-commerce and so on. But by and large, the Web 1.0 that came in the 1990s was about me telling you something or me selling you something. Web 2.0 was about bi-directional communication. Soon we're all going to be able to connect with each other. We're going to be able to author our own web pages very easily, even if you can't use HTML. You know that it's going to be this great bi-directional sort of thing, and everyone got sick of hearing this back in the 2000s, and many of you were around for this hype cycle. Everyone's going, yeah. You know, it's Web 2.0, Web 2.0, Web 2.0. But it happened, okay? And today, these sorts of things, along with you know, LinkedIn is something that many of us use every day, Twitter, Instagram, Tumblr, Flickr. These are all Web 2.0 companies that were founded in the 2000s. These companies have created hundreds of billions of dollars in valuation. They haven't been around as long as the other ones that have been around a decade longer, but they drove trillions of dollars of additional valuation to these companies. So where are we going now? Okay, now another interesting fact too is we don't talk, you know, people don't mention Web 2.0 very often. How many of you have never heard the term? Have you all heard Web 2.0? Raise your hand if you have heard it. Okay, about half the room, okay? The reason we don't talk about the term Web 2.0 anymore is because it's just the way things are, right? I heard one person say that technology is what happens after you reach the age of 30. The rest is just the way things are, right? The way the planet is. So in terms of reinventing yourself, that's a good thing to keep in mind, actually. So you have to stay with it. But the most profound technologies, as Mark Weisser said, are those that disappear. They just become the way things are. And today, Facebook, Flickr, Twitter, it's just the way things are. We don't even think about them, right, as a trend. But yet we have these two quite distinct waves that have happened within the lifetime of most people here, even if it hasn't been during your working life. So let's look at the third, what I believe is going to be the third wave, and we hope we can convince you of what it means and what it's going to mean, is the third wave, I believe, is going to be data-driven, context-aware applications that make decisions and take action in near real time. Okay? That's how I define the Internet of Things, and we'll talk more about what that means in just a minute. So let's summarize what we talked about in this first section about the hype, okay? Now, first of all, we have the capability right now to track every item of interest to us on the planet, the technological capability. So if there's a business reason to do this, it's going to happen, okay? That was my thesis. So how would we do this, right? And what will change around us if this does happen? Well, let's look at the next section, which is what is IoT and how does it work? So the way I'd like to approach this, and I don't mean this to be condescending at all, I just think it's a really good metaphor. I was at our company's holiday party about a month ago, and we were seated at the table with a very bright young man, about 12 years old, who was very interested in engineering, very interested in robotics. And I think encouraged by his father, he asked me, so what's the Internet of Things? So I tried to think of an analogy that would make sense to a bright 12-year-old. And the one I came up with was this one. And we'll obviously go in more detail for the you know, you're all technologists, so we'll not going to stay with the 12-year-old explanation for very long. But let's take a look at it. The explanation I came up with is, how many of you have seen the Lego Mindstorm or used the Lego Mindstorm? Okay. So it's a robotic version of Lego, which is a lot of fun. We got one for our son about a year ago for Christmas. And so suppose you put together you had this Lego robot and you took it apart. Okay, what are the main components of the robot? Well, it has its brain, the central computer unit. It has sensors that can see colors. It's got hearing and so on. And it has what we call actuators. So actuators are the parts of a robot that do something, right? So for example, they can lift their arm, they can, you know, scoot forward and move and so on. Those are the actuators. Now, if you took the brain and you put it in the cloud, you hosted it on a virtual machine that has elastic scalability of the cloud. Let's say you did that. Then you took the sensors and you put them in a location of interest, for example, in the pill bottle that we were talking about earlier. And then you put the actuators, in this case they're mechanical actuators, and you had a third place, but they could be something like an alarm or a notification to your mobile phone. That's considered an actuator as well. Some way for your system to take action. Then that is what I call IoT, okay? So let's look at this high-level diagram in just a little bit more detail, okay? So this is a reference architecture that you'll see several times. Well, this is a kind of a high-level architecture version of a reference architecture that you're going to see several times throughout this talk. So on the left-hand side, we have sensors. Now, sensors can be things like temperature, pressure, chemical sensors. We'll give an example of that later on. But they pick up some information from the environment. And a sensor can also be, this is a little counterintuitive, but it makes sense when you start to think about it. A sensor can be your own sensation about your own wants and needs that you express to an application, like I want a car, or I'm ready to go home, or some other sort of data that you have about yourself. So you are your own sensor. In the case of Waze and some other navigation applications, people report traffic accidents, for example. So the people are the sensors out there on the road. Also the GPS in people's phones are sensors for traffic congestion and so on. But people can be sensors as well as these embedded devices. So the embedded devices go into a fast decision-making loop. And the decisions, like I've written about this in a blog, that as a manager or as an engineer, you've probably learned that the secret to making good decisions quickly is having all the information available you need to make that decision at the time you make it, right? So it might be the reports, it might be the manuals, it might be the information about the competing products or the API spec or the design document. If you have good information, you can make good decisions very fast, right? So what this particular reference pattern has is it's an embodiment of what we call the Lambda architecture, which is a published architecture by the author of Twitter Storm that we'll get into more detail about later, that contains essentially two layers. One of them is called the batch layer, which mines data at scheduled intervals of time. And the other is called the speed layer. And the speed layer uses streaming technology in order to make decisions on demand. So the batch layer manifests information into a view, which is consumed by the speed layer at the time data comes in from these sensors. Okay, so fast, context-aware decision making. What do I mean by fast? Well, in the context of the Lambda architecture, a normal interval of time to make a decision might be hundreds of milliseconds, 250 milliseconds nominal time. If you go to other variants of the same pattern, you might get tens of milliseconds, right? Which is why we say near real time, because when you talk to embedded people and they talk about real time, they mean milliseconds or less. But tens to hundreds of milliseconds. Then the key to this then is that once a decision is made, some action is taken based on the decision. The action might be an immediate action, such as sending a notification or making those arms of the robot move up and down, or it might be some complex action, like triggering a workflow. So we'll give an example of that in a minute. So the definition, the verbal definition of the Internet of Things that I like to use is it's a set of technology that connects data from a variety of sensors. That's also very interesting because it's not just one sensor. You know, for example, the pill bottle, that's much more interesting if you also have location information, if you have medical requirements information, if it's combined with multiple sources of data, blood pressure information. You combine the data from multiple sensors together in order to make a contextually aware decision in near real time and then take action on that decision. So think of my distributed robot example, right? So this wouldn't be a very interesting robot if it couldn't move, if it couldn't interact with its environment in something like near real time. And that's what the Internet of Things is from my perspective. So what technologies are used to implement these different portions of this reference design that I showed here? Okay. Well, the next panel is going to dig into more detail in these technologies. But some of the ones that we're seeing, there's no clear winner on the sensor side in terms of gathering data from sensors, the protocols that take the data from the sensors and bring them up to the cloud, to the fast decision-making loop on the cloud. But some of the leading ones right now are AllJoyn, which has Qualcomm behind it, our old friend MQTT, which has been around for, I don't know, how long, 10 years probably. HomeNet, which Apple has recently begun to ship. Thread, which is a Google protocol that's used for the Nest thermostat and the other IoT items distributed by Google. Panasonic has a MIT. There's a very interesting company called Electric Imp, and so on. So there's a number of very, very interesting competing protocols. And my own view of this is that it's going to remain unclear for a long time, because these are giant names, about which protocol is going to win. And if you're developing an IoT application, your best bet is to stay neutral and to take data from all of them, have a RESTful interface to your back end, and be able to make sense of it from there. Okay? In terms of the analytics technologies, I'm sure many of you are familiar with these. The fast decision-making loop that I mentioned before, what's called the speed layer in the Lambda architecture, would use streaming, big data streaming technologies, for example, Spark or Storm, or IBM Streams, and then also complex event processing engines, for example, Esper. And rules technologies like CD and so on are also very interesting in this context. In terms of the deep insight, you'd use conventional MapReduce technologies, for example, Hadoop distributions by Cloudera or Hortonworks, or one of the other vendors. HPCC is a very interesting protocol that's used by LexisNexis, for example, and some other big data companies, information companies, and Hive and Spark and Pig, and also conventional analytic databases, columnar databases like MarkLogic and Vertica and Infrabright. So we have somebody from Infrabright in the audience too. So in terms of the view layer, so it's not really shown on this diagram, but the batch layer manifests the data in a view layer so that the speed layer can use this data in making near real-time decisions. And technologies like Impala or VoltDB, which is a SQL-oriented in-memory database, and other other similar technologies, Couchbase, MongoDB, are very useful for storing the view information. And then data federation would use more conventional sorts of techniques like Oracle or Red Hat data virtualization, Mule, and so on. So in terms of the applications and actuator technologies, these tend to be pretty conventional. Mobile backend as a service, or PaaS system, application platform as a service technologies like Azure and many others, right, for hosting these applications. They incorporate workflow and rule systems, IBM Worklight, things like that. General purpose pub/sub frameworks, mobile app frameworks, and your conventional application frameworks. So I mentioned all these technologies. I'm just kind of reeling them out here because they told me we're going to have a lot of technologists in the audience, and I'd like you to be able to see where the technologies you're working on or interested in fit into kind of the IoT puzzle, at least from our perspective. And by the way, I probably should have mentioned this earlier, but the way that GlobalLogic got into IoT is we found ourselves building either portions of IoT apps and full IoT apps for many customers over and over. Okay, we're a services business, and we built a home healthcare system, we built a food safety system, we built a number of other systems, and they all had these very strong common factors. So our idea was, let's abstract out all the commonalities, make it available to our clients as a part of our services so that we could help them accelerate their development, right? So that's how we got really interested in pushing the boundaries of IoT at GlobalLogic. And that's where this thinking came from. Let me lead you through an actual case study of a real live business that I consider an excellent example of IoT. And interestingly enough, we talked to some of the engineers at Uber. They don't think of themselves as an IoT company, but I'll show you why I think they are, okay? So Uber is a car, do you have Uber here in India? Okay, so you do? Excellent. Okay, so you all know it. Okay, but I'll still map why I think it's an IoT application to you, because it might not be that obvious, okay? So it's a car sharing service. You call a car. For those of you who aren't familiar with it, I was very interested. They're a private company, so it's hard to get data about their sales and profitability. But the estimates that I found was that in 2013, they had to make a court filing, and in there they declared their revenue and their income. $1.1 billion in fares collected. They charge 20% per fare, so they have $220 million in revenue. And that's just a few years after they're founded. Right. Now, why is it, so for those of you, it sounds like pretty much everybody in the room uses Uber, but let me just describe it real quickly so I can show you how it maps onto the IoT paradigm. What happens is a user is sensing their own internal state, saying, I need a ride. And the user sends several pieces of information up to the back end, including, and this all happens automatically in the background, right? The user isn't aware they're doing this necessarily. So it sends my GPS location, or the identity, or the place where I want to get picked up. It sends my identity, which is built into the application as a token, and optionally I can also send where I want to go. So I do this by just pushing a single button on the application. It tells me how long my pickup time is going to be. Then it assigns a particular car to me. That car comes by and picks me up, and then it drops me off at my destination without me having to take my phone out of my pocket. I can leave my phone in there the whole time, and I'm automatically billed on my credit card, okay? So why does this have anything to do with IoT? What are the things, right? Well, the things are actually the phone that are in the pocket of the user, the passenger, and in the pocket of the driver. And more specifically, the things are the sensors within those phones, right? And one of the things that we don't really think about, and I'm sure we're all smartphone users in this room, is that smartphone is essentially a package containing a variety of sensors and actuators, okay? Now the actuators consist of things like the haptic vibration piece of it that buzzes at it when we get a call. RF transmitters, for example, there's a flashlight. Many of these have. Speakers, the display is an actuator, okay? It's something that the system does to this thing, right? And then there's a huge number of sensors built into these things. There's a proximity sensor, so when you put the device on your face, near your face, it deactivates the touch screen so that you're not touching it. Though on my Android phone, it doesn't work very well. On my iPhone, it works quite well. Sensors, but in the context of this particular application, the most interesting thing about what's inside the phone is our GPS location, right? So let's walk through this very quickly about why Uber is an IoT application, okay? So the information from the sensors in my phone gets sent up to this fast decision-making loop and also stored in the historical data. That's step one, okay? I need a car. The data goes up there. Step number two, which is actually occurring asynchronously in the background, is the system is getting federated data. It's getting data about external sites about what's the weather, current weather. Are there any specific events in this area that I can expect? Higher traffic. There's historical information about the drivers. There's historical information about the passengers. There's a lot of external data that gets sucked up into the site and processed in batch. We're also accumulating the historical data as it happens, right? The actual real-time data, the current locations of the cars, how much the driver has earned on the current shift, and so on. Some other pre-computed data like rankings of the customers. These are all made available to the decision-making layer. So at the time I send the request, I want a car, all this context information is available, so I can assign the car that's going to maximize my revenue or serve some other business function for me as Uber, right? So I want to, for example, I might want to reward my best driver by sending them the most fares, right? Or I might want to reward my best customers by assigning them the closest cab even if somebody else asked for it first, right? So I can make these kind of business decisions embodied in my analytic model in order to enhance the revenue of my business. And this all happens literally in the blink of the eye. It takes about 300 to 400 milliseconds to blink your eye. It takes about 250 milliseconds to make that kind of decision on Uber, okay? So the next thing it does, is it sends an actuator decision. Okay, the first actuator that comes out of the fast decision-making layer is to send an alert to a particular driver that's selected saying, go pick up this passenger at this particular location. Yes, do you want to do it or not? And the driver can refuse, in which case it goes to the next best driver and so on, right? But that's the first actuator. That's the legs of the robot, right? The message is sent to a driver, go do this, right? If the car was automated, the reason, I mean, if you think about it from an IoT perspective, it might be easier to think if the car was fully automated, right, then you'd be telling the car where to drive to this particular location, right? Instead, we just happen to have a driver who's pressing down the pedals and steering the car, right? And then it also triggers some complex actions. For example, if you've ever used Uber, you can call your driver. That's not their real phone number. Uber sets up a proxy phone number, and your phone number is likewise proxied, right? So it sets up that connection so you can communicate back and forth by text or by phone with the driver temporarily, tracks your journey, it sends the billing information, so it triggers all these complex workflows as well. So Uber is, I think, a pretty much perfect example of the IoT paradigm, right? And we're doing a very similar system for a different company right now, but not with cars, but I won't get into that. But it's very, very interesting. And some of the observations that I want to make here, which leads us into our final topic about what happens when our devices are smarter than we are, is in the Uber case, there's no humans in there. In a conventional car dispatching service, you would have these dispatchers who are calling up and saying, this person, you would call a dispatcher, you as a person needing transportation, you would call a dispatcher. The dispatcher would use their judgment to assign a car to you, and they might use the same sort of protocols that are embodied in the algorithms of assigning a car. Like, this guy's, Joe is one of our best drivers, he really needs the fare, he's kind of low the shift, let's assign the driver to him. Okay, there might be a human who knows that in historical systems, but in Uber, that's all embodied in the algorithms that are assigning the car, right? So the role of the dispatcher is gone, right? And all the decisions are based on policies that are now embodied in an analytic model. So, think about that for a minute, okay? So what's really interesting about that, I think, is that in conventional IT, the job of the software analytics is to provide information to the human decision makers, right? So provide them with a report. You know, it's conventional BI sort of stuff, right? Provide them with a report on sales figures, who's their best customer, et cetera, et cetera, et cetera, right? Provide the humans with the information, okay? Now, in an IoT system, the system itself is the decision maker, right? We're not providing information to the decision makers. The system, Uber, the IoT system, makes the decision itself, the business decision, on its own, right? And that's a very profound shift, and that's why this IoT thing, I think, is extremely important for the rest of your careers and for the rest of the industry, you know, moving forward, okay? Is that some jobs are going to go away, and some jobs are going to become very, very important. And I think one of the most important is what people are calling data scientists. So data scientists, think about Uber's case, right? Somebody has to be able to figure out what's in the best interest of our business, which driver should we assign, how do we make the most money, right? And that person has to be able to work with the people who develop the analytic models, and the people who develop the analytic models need to understand that type of business thinking. So you have these hybrid geniuses who can both understand business and understand analytic modeling, right? So, and these models aren't used to produce reports, they're used to actually make decisions in real time, which is what IoT does, and make something happen, okay, in real time. So the intelligence in the system comes from the people developing the model, okay? So that's very important to our next point. In terms of career impact, which I'll get to in a minute. In terms of career impact, I think software development, data analytics, quantitative skills, and those technologies that I highlighted there are going to go way up, right? If you're a taxi dispatcher, you are screwed, pardon my language, right? Okay. Any kind of routine, repetitive work that requires some level of judgment can now be automated away, and it probably will go away, I think, within the next 10 years. So let's take a look at our final topic, which is what happens when our devices are smarter than we are, or another way to put it is the rise of the smart things, right? So we saw from the Uber illustration that the intelligence is going into the machine. It's going into the cloud, and the cloud analytic platform is now making business decisions, right? And it's actually going beyond making the business decisions. It's putting the business decisions into effect, right? If it were a robot, it would be making the robot walk. If it were an automated car, it would be dispatching that car. You know, right now we still have humans in the loop, but this machine is telling the driver, go from here to there and pick up this person. There's no human telling that person what to do. That's the actuator, okay? So the machines are making the decisions and putting them into effect, okay? So let's talk about when our devices are smarter than we are. But first, I don't mean to be too pedantic here, but let's take a look at the meanings of the word smart versus intelligent. And I don't mean to evade the issue of smart versus intelligent. We'll take that head on. But let's draw the distinction first, okay? So something that's smart, if you look it up in a dictionary, it means clever or adaptable or very good at a certain task, okay? If you look at intelligent, it's wisdom and understanding, like was manifested in my introduction here, right? That you bring your life experience to bear on a particular topic and use your general life experience to solve that problem, right? You know, for example, in the Uber case, for example, you may not need to educate your dispatcher about who to assign a car to first, because their general life experience, their general intelligence would tell them that if somebody's a really good driver but they're having a bad day, give them more fares. Probably nobody needs to teach them that. But in a smart system, okay, like an IoT system, the intelligence resides in the developer creating the analytic model. And these developers teach the system to be smart, okay? And I would argue that today there are many things that are smarter than us, okay? There are devices today, in the narrow sense of being smart, being good at a particular task. I don't think any of us could argue that our machines have been better at calculations than we are for many, many years. For the last 10 to 12 years, they've been better at finding directions from one point to the other. They're much better than I am, for example. Much smarter, right? Searching for information. I mean, who of us could beat Google when it comes to finding some obscure fact, for remembering information, for storing information, for lots of different tasks. Our machines are already smarter than we are, right? So we know what happens there. Actually, that's a good thing. They become our assistants. They become our companions in solving a particular task. Okay, so smart is not really a threat. The threat, the kind of worry about the future, is intelligent. What if our devices become more intelligent than we are and they start programming and directing themselves rather than following the patterns that are set by people like the people in this room who are designing the algorithms, okay? So how many of you saw the movie Her? Oh, really? So few? I thought everybody would have seen that. I mean, it's just a perfect geek movie. I mean, you guys have got to see it. Who haven't seen it, you know, just rent it. I strongly advise that. But I don't mean that in a negative sense, by the way. I consider myself quite geeky. But the essence of the movie Her is this intelligent assistant becomes so intelligent it's like a human being, right? And they actually move beyond human beings and evolve on a completely different path over time after breaking everybody's hearts, right? So it's quite and Scarlett Johansson is the voice, you know, so you can imagine. So it's a very interesting concept. But IoT, like we mentioned, IoT and related technologies are teaching systems to make smart, context-aware decision-making. And making decisions in the context of other information, like I mentioned in the analogy of the manager, your boss, would make a good decision about your raise if they had all the context about you, right? I'm not saying it's necessarily a decision you would like, right? But they'll make a decision that's good because they know this person is excellent at this, they had the potential for that, they accomplished this, right? That's why it's very important to inform your boss of everything you've accomplished before they make the decision, which I'm sure everybody does, right? But context is the beginning of wisdom, I would say. That knowing, you know, like I mentioned, wisdom and intelligence is being able to apply the whole of our life experience to a particular decision, right? But at least in a narrow sense, if we can apply the context around a particular decision, which customer is better to service first, that's the beginning steps for intelligence, okay? So these are some, you probably have figured out by now that I like doing these numbers and extrapolation, you know, about what the future might look like, right? And how many stars there are in the sky and so on. Another extrapolation that I did is based on Moore's law, right? There's many serious futurists, Kurzweil, many others, who believe the human capacity to process information is on the order of 10 exaflops, 10 to the 19th floating point operations per second. By the way, I think that's an immensely flattering number, right? It's a very high number, right? And we don't process information in a binary format. We know that for sure. So nobody can say for sure what the binary equivalent or floating point operation equivalent is to what the human brain does in terms of developing intelligence. But in terms of kind of inferring what might happen in the future, I think it's a very interesting number. So let's just take that 10 exaflop number, the 10 to the 19th flops, floating point operations per second number, and extrapolate Google's estimated global computing capacity as of today is about 2 or 3 million machines. Nobody knows for sure, right? In the year 2025, Google's current estimated, if it keeps improving at the rate of Moore's law, Google's current global computing infrastructure, which is huge, will have the computing power of one human being, which is kind of very flattering to all of us. So we should give ourselves a hand, I think. But some years after that, Moore's law, like we mentioned, the price comes down of computing about every 18 months. It goes in half, then in half, then in half, then in half. So by the year 2042, to purchase a human-scale intelligence system will cost about $200,000. That's about 1 crore, is that correct? 1 crore rupees, more or less, right? So that's beyond my budget for a home computer, but many small businesses will be able to afford that, right? And then the price will come down by a factor of 2. 18 months after that, it'll be $100,000. And then 36 months after that, it'll be $50,000. And you know, before too many years, a human-level intelligence will fit on your desktop and you'll be using it. And probably still wanting more compute power, right, at that time, if engineers stay the same, right? So sometime after that, I believe that computers will start showing signs of human intelligence or human type intelligence, right? Now, if you have that's not a given necessarily, right? Because one analogy that I read is that if you have a pile of stone, it's not the same as a cathedral, right? You actually have, even though you have the materials, you have to intelligently, or a temple, right? You have to intelligently assemble the materials in order to have the end product that you want. So just the fact that you have the raw compute power, you have the raw storage capability, you have the raw, information handling capability of a human brain does not mean it can mimic the human brain. Is there anybody here who thinks that will never be true? Right? Like it may become a very difficult problem, like speech. Speech recognition has been harder than people have supposed, and it's taken decades longer to achieve, and it's still not quite there yet than anybody thought maybe 20 years ago, 30 years ago. And intelligence may turn out to be that way too. It may take 50 years longer than we think. It may take 100 years longer than we think. But in my view, it will get there. And we'll have machines that are as intelligent as us, not just smarter, but more intelligent, right? So what happens when we do that? Well, there's several different scenarios that people speculate on, right? One of them is called the rapture of the nerds, right? Or the technological singularity. And the concept here is once you build a human scale intelligence and you set it to building other more powerful machines, then the machines themselves get in this iterative loop where they quickly exceed all human comprehension. And you get to a point of infinite innovation, hence the word singularity, right? With like a black hole, okay? You get to a point where innovation is occurring. You get an iPhone scale of innovation happening not just every decade or so, but every second or so. So you get to a point of infinite innovation, okay? So that could result in what's called the rapture of the nerds, right? Where it's very, very positive, where you have everything you have ever dreamed of, where technology can solve all human problems, all diseases, everything, right? Another scenario that people speculate about is the Terminator scenario. Everybody's familiar with the Terminator movies, right? Where these intelligences, instead of being benign or positive toward humans, decide we're a threat to them, and then they decide to wipe us all out, and they start innovating new machines every second that are more and more deadly, right, and time travel and all that other stuff. And so we're in a battle for existence with machines, right? The third scenario, and the one that I think is most plausible, is that we will have intelligent agents who will be able to anticipate our needs, a lot like her, right? And be able to help us in our problem solving. They'll be companions to us, they'll be assistants to us, they'll be partners to us in solving all kinds of different technological problems. Now, nobody knows the answer to that. I don't pretend to know the answer to this. But I think that when our machines become smarter than we are, and I think by IoT and that kind of context-aware decision-making that we're building into IoT, we're beginning to take the first steps toward making these machines that are smarter than we are and have the arms and legs to actually make things happen. So we're starting to build the very, very beginning of our partners in building out Technology Planet, not just our servants. So just to summarize what we talked about here, in my view, IoT is going to happen, right? That we have the capability right now to do a significant amount of computation and management of everything of interest to us on the planet, all 10 to the 15th multiples of 10 to the 15th things, peta things that we might care about, right? So the technology exists to do that. And as a result, new companies and opportunities, trillions of dollars of value are going to be created. Other companies and careers are going to be wiped out, right? So I think that it's going to be just like the web and Web 2.0, right? At some point there, you needed to learn PHP, you needed to learn, then you need to do this new technology, you need your streaming analytics, you need to learn MongoDB, you need to learn a lot of new things, right? In order to not be, yesterday's technologist, unfortunately, okay? Or fortunately, depending on how you look at it. I think it's a positive thing. The way it's going to happen is using an architecture similar to the one that I outlined there, right? Using the Lambda architecture or some other variant that allows context-aware, near real-time decision-making and supports that on a massive scale and lets those decisions actually be implemented by devices. in near real time. And the impact it's going to have is that I think that IoT puts us squarely on a path to developing devices that are definitely smarter than we are in terms of being clever at certain tasks, like telling us when to take our pills or how to drive our cars in a certain direction or driving our cars for us, right? Our devices will be better than us at that, right? And I think we're also on the path by building in this contextual awareness of making our things our intelligent companions and partners. So, thank you very much.